You may have heard of noise-canceling earphones. You may have even used some or own a pair. And they're really cool devices, but many people don't understand quite how they work. They're thinking they just kind of muffle out the noise. But they're actually an active process to cancel noise. And therefore, I'm going to use them as an example of wave interference. Okay, so to do it, to understand how these noise-canceling earphones work, suppose that you're listening to your music and there's some sound from a computer fan or something that's coming, and you can hear it. Okay, and so it's coming through your earphones, just around them, or the sound is able to pierce through it and get to your eardrum along with the music you're listening to. Okay, so I'm going to represent the source of that sound as, here's my speaker cone. This is my traditional or standard speaker cone. I'm going to draw an equilibrium line here, and I'm going to assume we have this sinusoidal wave coming out of it, traveling this way. Okay, so your ear is over here somewhere. All right. Now that's entering your earphone. Let's go ahead and place your earphone. Okay, we're going to place your earphone right here. So this is another speaker. There's another speaker. That's what your earbuds are. Your headphones are, and it is a speaker playing some music. Okay, now the way noise canceling headphones work is that they have a recorder in them as well. So they're playing the music that you want to listen to, but they also are recording what's coming in from the outside. Okay, and then what they do, in an instant of time, they process that and send out, in addition to your music, they send out the opposite of it. Let me continue this. Okay, they send out the opposite to what they just recorded. Okay, so this sound is coming in and coming into your ear. This listens to that and instantly sends the opposite of it into your ear. Okay, now you might say, oh, is that quiet because it's opposite? It's not quiet. It's just oscillating out of phase from this one. Exactly oppositely out of phase of this one. And if you're now well versed with how waves add together, if I look everywhere along this length, I have a positive displacement that is canceled by a negative displacement at every position along this. And so what the noise canceling headphones have done is they have actually added noise to your ear, but they have done it in just the right way such that the net displacement of the air molecules caused by the true noise and what they have generated cancel out, and then leaving only the music noise or the music waves coming into your ear. It's a really cool technique. So it's actually adding noise to make silence. A cool principle to think about. All right, so what we want to do is try and make this a little bit more quantitative and think about it carefully. In this particular case, the way that works is this has a phase. I'm going to call this speaker 1, this speaker 2, and phase 1, the phase constant for 1, so phi0, 1, in this case is 0. Okay? We have no phase because it's a perfect sine wave if this is our t equals 0 picture. All right, and we have let's pick any point. I'm going to go ahead and pick this point I've drawn right here. Okay, we have a distance from the speaker to that point. Call it x1. Okay, and the distance from this speaker to that point, I'll call it x2. And this speaker has a phase constant of pi. Okay, it's shooting down from the equilibrium point when this one's shooting up, so it's out of sync by half a cycle. So phi02 equals pi. All right. Now the goal, the distance plus the phase at a certain time is equal to, phase constant is equal to the overall phase. Okay, and the goal for these to cancel is you want them to be opposite each other. All right, and so what we have is we have the difference in x1 and x2 is one wavelength. We can see that these speakers are separated by one wavelength. Okay, so our delta x between the two equals lambda, and our difference in phase constants, delta phi0, is equal to pi. Okay, so what is that going to do? Well, if this in the total phase equals a half cycle, or 3 half cycle, or 5 half cycle, then they should cancel out, okay, as we can see here. And so the phase, okay, the change in the phase between the two is the 2 pi times the change in the position over the wavelength. That's the first term from our displacement equation inside the sign argument. Okay, and then we have to add the difference in the phase constant. All right. Now there's no minus omega t here because that's the same on both, and so we're canceling that out automatically because time's the same, the wavelength's the same, and the which means the frequency is the same. Okay. So what we have here in this case is our delta x is lambda, so that means these cancel, leaving me with 2 pi, and our delta phi is pi, so this equals 3 pi. Okay. So we have a phase difference, an overall phase difference between the two waves of 3 pi, which is a half cycle out of sync. And so when this one's up, this one is down. So this we call destructive interference. Okay, well, let's take a case where we change it just a little bit. What if we have our original sound, equilibrium line, it's unchanged. Okay. And now what I do is I reverse roles here. What if I place a speaker? So this isn't how noise canceling earphones would work, but we could still achieve interference by just simply placing speakers in different locations. What if I now place the speaker right here, but have it broadcast in the same phase as this one? So this way, it's coming out, down, like that. So now as I look here, the change in position, the difference in position is half a wavelength. Okay? But the change in phase, so this phase is 0, so phi 01 is 0, and phi 02 equals 0. And so when I look at the total change in the phase, that is equal to 2 pi delta x over lambda plus my delta phi 0. Now that's 0 because they're both the same. And this one is now lambda over 2. So the lambdas cancel and the 2's cancel, leaving me with pi. So this equals pi. So these have an overall half cycle difference, which is again destructive interference. Okay. So destructive interference is the case where our change in phase, okay, which will equal the contribution from how far apart the sources are as a function of their wavelength, or what fraction of a wavelength, plus how different their phase constants are. If that equals, okay, so if that equals pi, or 3 pi, or 5 pi, then we get destructive interference. They'll cancel out completely. Now, if we set our speakers' positions or their phase such that this equals 2 or 0 or 2 pi or 4 pi, then we get constructive interference. So this equation right here relates the phases between the two sources together, and it's important to note it's in terms of either a path difference or in terms of a phase difference, phase constant difference, or the sum of the two. So in the case down here, our path difference was off by half a wavelength, but our phase was not. But we still had an overall pi. Up here, our path difference was a function was one wavelength, and so a full 2 pi cycle. But it was our phase constant that was off by pi, which gave us that odd pi in addition.